So far, we understood or have some understanding of the benefits of scaling. We saw things are going to be different, but we are motivated by the fact that we can make things smaller and faster and lower power, and at the same time, hopefully cheaper. And then, we saw that these are the motivations behind the whole microelectronic industry, and later on, MEMS and microsystems. All of these are pushed forward by the fact that we can make a ton of these devices with good performance at very low costs. Now, we talked about the sequence of processes that you have. We said that you have to have a wafer, and then you deposit or grow film on it, and then you transfer patterns to this film, which basically later on translate into regions that you want to dope differently, or regions that you want to cut out and structure your MEMS device, for instance. So in this lecture, we're going to talk about lithography, which is the process of transferring those patterns onto your film, on top of your film, basically defining the pattern that you want from that film. And then the next topic will be etching, removing whatever that we don't need from those films. And then that closes basically the list of the requirements that we have, or processing steps that we need to create the process flow and make microelectronic or MEMS devices. So going through the processing steps again, you have seen this a few times already. The idea is that the MEMS designer or circuit designer gives us a set of drawings. These are called layouts, right? So these drawings tell us, the process engineer, that each layer that you have on this film, in this process, when you deposit it, what should remain of it at the end of the process. So there is a drawing that says, keep this much of the oxide, keep this much of the silicon, and so on and so forth. And the layout is created by the MEMS designer, has all this information in it, has all those aligned layers on top of it. Then it comes to the process. And then when we are doing the processing, we first of all go and create a set of masks based on the layout, right? So each drawing for each layer becomes a pattern on a mask. These masks are essentially glass plates with chrome drawings on them. We'll talk about how to create these masks. But for each layer, we have the corresponding drawing on a glass plate from chrome, using chrome lines. And then we go and pick our substrate, deposit the films or grow the films that we want on that substrate, and then define the patterns. And where on this film we want to keep and which areas we want to remove. The step after that is material removal. We go through this sequence many, many times depending on the process. Microelectronic processes are usually a bit more complicated, so you may go through this maybe 20, 30, 40, 50 times. MEMS processes tend to be more simple, and therefore you only go through this maybe 5 times or up to 10 times. Then sometimes we do a doping step here and there depending on the requirements for the electrical properties of the film. And then at the end of the story, for a MEMS device, we need to have some protection to basically save it from the environment, protect it from the environment, and dice, package, and sell it. Now, all of these steps are taking place in fabs that are called clean rooms, or these facilities, we call them fabs, and they are made of clean rooms inside. And we are going to talk about why we need clean rooms. Why can't you do this in regular spaces, in a regular lab? Why do you have to do it in a clean area? And we also specify what clean means. Now, here is a short video about how one of these fabs look like. And actually, if you look at this, you'll note this is not very new. This is from a few years back. But you'll notice the amount of automation that is going on in these manufacturing facilities. And this is, in this case, a microelectronic fab by Intel. These are truly mechatronic facilities. You have a ton of mechanical things going on at the same time as you have to have all sorts of robotic and monitoring capabilities in there. Plus, there's a lot of gas flow and liquid flow and thermal control and all that. So this is as complicated as it gets. So let's just watch this video. It's a quick one. The rest of the videos in this lecture, I've provided the links to them on our course website. And the links are also provided on the slides. You can just go and look at them in your own time. I suggest that you do that because I think you're going to have a better quality video if you just go and click on the link or look at the link as you go through the slides rather than having to look at them through the presentations here. So let's watch this one. This is a fairly short one.
Sophisticated manufacturing process in the world, and it's probably the most automated manufacturing process in the world. And so that in itself is challenging. We're always on the cutting edge. Our wafers are 12 inches in diameter, and we move 25 of them at a time in a box. And it just weighs too much for one person to do repetitive moves, so we had to automate it. When we talk about the vehicles, it's part of our AMHS system, our Automated Material Handling System. It's the transportation vehicle that picks up the product and delivers it to the process tool. It takes it from the process tool and delivers it to the next process tool. If the tool's not ready, it puts it in a storage unit. We keep track of the priority of what needs to move where first. We know where all the product is in the factory at any given time. In the old days, if our automation went down, it probably wasn't as important. The factory still ran. But today, if major parts of our automation system goes down, the factory stops. I think what excites me about what Intel does is the computing capabilities that we make possible that make people's lives better and more enriching.
Okay, one thing you notice is that there are actually no humans where the actual work is happening, where the actual chips are made. All the humans that you saw in the video are in the support rooms, is where the equipment is basically connected to gas lines and you're basically outside the actual manufacturing area. And there's good reasons for that. We'll talk about that. Here is what we mean by cleanness. So we want to make sure that when you're making these devices, at the very least, you do not have particle contamination, right? So this is the issue that typical particles in the air are on the order of, let's say, a micron, half a micron, 2 microns. These are particles that you do not see, but they exist. So in a typical room, you have millions of them, let's say 1 million of these particles that are, let's say, about half a micron or larger in diameter in every cubic foot of air. Now, if you make your MEMS device or MEMS wafer or microelectronic wafer, if you make it in an environment like this, it's inevitable that some of these particles will land on your wafer. And then if that happens, well, that's usually the end of the story for your device that is just underneath the particle for several reasons. If this happens during the processing, we are going to see that it can actually mask the information that was on your mask. Right? So you can basically get another layer of, let's say, image protection from this particle that wasn't intended and that can ruin your device. Basically, the device is made in the wrong way. In case of MEMS devices, a single particle can actually disable the device. So let's say you have done the fabrication, you're done at the end of the story, a particle comes and lands on your device. If you're unlucky and it hits one of those important regions on your device, let's say between capacitive electrodes, that's all that there is needed to basically render your device useless, right? So in order to have enough number of devices survive the process, the manufacturing process, so that the entire process from beginning to selling a chip is economical, you need to maintain a very, very clean environment. So we call these rooms which have super clean environments, clean rooms. The degree of cleanliness is specified as how many particles of a diameter of half micron or larger you have in a cubic foot of air, right? So a class 1000 clean room, let's say, has 1,000 particles that are half a micron in diameter or larger in 1 cubic foot of air. And notice that you're going from about 1 million particles in that same cubic foot to about 1,000. So that's 1,000 times more, let's say, in terms of particles, pure than regular air. For your typical manufacturing facilities, you need something on the order of class 1 to class 10. If you go to microelectronic facilities, they're actually class half, it's better than class 1 nowadays. And for that reason, the definition for how clean a clean room is, this is an older definition based on the number of particles of half a micron or larger in a cubic foot. The newer definitions takes into account the extra cleanliness that is required for these clean rooms. But this one is easy to basically visualize. So class 1 means that you have one particle of half a micron, that is half a micron in diameter or larger per cubic foot of air. And now what happens is that, as we're going to see, photolithography is the most sensitive process to contamination, because this is where you're defining the different sections of your device. If it is a transistor, you're defining where the gate, source, and drain are. If you're making a MEMS device, you're defining where the beam is, or when the springs are, or where the edge holes are, right? So all of those are very, very critical points. And this is the stage that if anything goes wrong, if you create the wrong image for that given mask, your device will most likely fail. And that reduces your yield. Yield being the fraction of working devices to total number of devices on the mask, right? So typically for microelectronic devices or circuits, we would like to have yields on the order of 90% or better. For MEMS devices, we would like to have yields on the order of 70% or better. So 70 out of 100 devices on that wafer should survive, okay? And if there is anything wrong at the lithography step, if there is an issue with your mask, if there are particles there, those devices will definitely not work. And therefore, usually the lithography area is the cleanest area in any clean room facility. Now, we also want to make sure that, yes, we're going to process this wafer in a clean area, but we also want to make sure that there are no particles on these wafers. And then typically, wafers go through a specific cleaning process in between the steps. So let's say you are done with, let's say, your etch, and you want to go and proceed to the next film deposition step. Between these two, what you do is that you clean the surface as well as you can. There are different ways of doing it. It's usually through harsh chemicals. Two of them are mentioned here, RCA clean and Piranha clean. So for example, in case of Piranha clean, what you have is sulfuric acid added to hydrogen peroxide. This is a very volatile, very aggressive combination. It removes all sorts of metal traces and organic traces from the surface of your wafer. And then the reason that you do this is that you want to make sure that for the next step in your process, you have the cleanest surface possible. Now, so on the next slide here, the issue is, what they're talking about is how a modern clean room is made. So I'm going to run this again during the lecture, but for the future, let's say we have 3 or 4 more videos for the remainder of this lecture. I would like you to watch them on your own. So in this case, so let's just run this. It's going to take a few minutes. Again, from Intel, not that Intel has the best facilities nowadays, it's just that they had more of this information online for everybody to view.
Fab 32 represents a strategic decision by Intel to invest in the future. It builds upon a tradition of innovative manufacturing leadership in the state. It represents an investment of $3 billion in manufacturing capacity and brings Chandler the most advanced chip manufacturing plant in the world.
Fab 32 is the next step in the legacy of high-volume manufacturing here in the state of Arizona. Starting with Fab 12 back in the mid-90s and then Fab 22 in the year 2000, Fab 32 will go into production the second half of 2007 and get fully ramped in 2008. We're proud to add to that legacy of manufacturing in Arizona.
Here are a few examples of what has gone into creating this facility. There are more than 568 miles of wiring, 137 miles of mechanical piping, and 75 miles of conduit. There are more than 8,000 tons of rebar, 11,000 tons of structural steel, and 86,000 cubic yards of concrete. This is enough concrete to pave a 3-foot wide sidewalk from the front door of Fab 32 to downtown Phoenix, a distance of 26 miles. But the most impressive thing about building Fab 32 is its people. It took more than 8 million skilled labor hours to construct the facility. That skilled labor translates into wages, which is fed back into our communities and supports the tax base of state, county, and city governments. Intel has a long-term commitment to the community. The benefits of Fab 32 began immediately at construction. To build the world's best microprocessors, Intel packs millions upon millions of transistors onto a chip in high-quality manufacturing cleanroom facilities that are automated as never before. These transistors are so small that even the smallest particles can contaminate the entire chip and ruin the processor. Consider this. This graphic represents a cross-section of a human hair, which is about 75 to 100 microns in diameter. The inner blue circle represents the limit of detection that the human eye can see, 40 to 50 microns in size. The black dot represents the fab construction certification, 0.5 microns, roughly 80 times smaller than what is visible to the human eye. Fab 32 builds microprocessors with features that are only 45 nanometers wide. Typically, when people think of an Intel semiconductor factory, they think of people in spacesuits in a clean room. However, the clean room isn't the only part of a semiconductor factory. There are many layers within the factory, with the clean room being just one of 4 critical levels. The top floor of the factory is called the pressurized plenum. This area handles and controls all the air filtration. On the roof of Fab 32 are multiple MAHs, or makeup air handlers. Each of these MAHs is about the size of a Greyhound bus and is responsible for the control and flow of air through the air cleaners and air scrubbers. Below the pressurized plenum is the clean room. For Fab 32, this is referred to as a ballroom fab. The areas are more open to facilitate faster movement and control of the product within. Next is the clean subfab. Here, support equipment, chemical and gas delivery systems are contained for the ballroom fab above. Finally, below the clean subfab is the utility level. This is where electrical and other support systems are kept and maintained.
We've got a unique perspective in Fab 32. 2 years ago when we announced the project, it was really only a plan on a piece of paper. 24 months later, we're on schedule and on budget of an almost $3 billion project. It's pretty amazing to watch the groundbreaking, the construction, the building activities, and now tool installation. Through that process, I've had a chance to work with some incredible, dedicated, and really talented people.
Fab 32 is like a city that never sleeps.
When we're making these products, we put them through a sequence of process steps. So the silicon goes through a sequence of steps. They get processed, they get work done on them in a piece of equipment or a tool. What we've done in 32 is recentered the entire organization around that tool. That tool runs 7, 24, 365 days a year. And so our organization needs to run 7, 24, 365 days a year. And we need to have, for the complexity of the process and products that we're making here, we need to maximize our technical talent around the clock. What's unique about the way Fab 32 is structured is that we have maximized our technician and engineering technical talent around the clock.
Fab 32's versatile employees are trained to execute their job functions flawlessly and to take initiative to solve problems before they occur. Its workforce includes experts and specialists such as chemical and electrical engineers, full-time nursing personnel, and emergency response team members. A typical factory day is 12 hours. When a technician starts a shift, he or she may be involved in morning operation meetings, running product, stretching, equipment maintenance, in-depth training, and involved in task forces to solve engineering and production problems. At the end of the shift, the technician will pass down to a counterpart on another shift. The process continues without interruption.
I want to be part of the best manufacturing machine on the planet. You've got to have the best process technology, you've got to have the best product, and then you've got to be the best manufacturing machine. And Fab 32 is set up to be the best manufacturing machine by leveraging the learnings in fab sort manufacturing over the past 2 years of not only the best technology startups and the best ramps that anyone can do in this business, but we are doing it at a faster pace and we are doing it at better costs than we've ever done historically.
The Fab 32 family would really like to thank our folks in construction, our folks.
Okay, so one thing that you may have noticed here is that one of these fellows that was interviewed said that there's a tool that has to work 24 hours a day, 7 days a week, because everything in that fab depended on that tool. And I can tell you that that tool is a lithography machine, right? We're going to talk about the different types, but this is the most critical tool that you have in your facility. Going back to the process sequence, you remember that, no matter what you did, you had to go through that lithography step in between, right? You had to go through this pattern definition step in between. It could be film growth, etching, all those things can be done at different places, but at the end of the story, they all come back to the same lithography machine and have that pattern definition step. So therefore, it becomes very, very critical, lithography as it is. Now, in terms of costs and what was mentioned, this video is already about 12 years, 13 years old, right? This is about the fab that opened in 2008 for 45 nanometer technology. If you are following the news in the field, now TSMC is producing chips that are 5 nanometers. 5 nanometer chips, basically the length of the channel in your MOSFET is only 5 nanometers, 9 times less, right? It's 13 years later. They were talking about a $3 billion investment in creating that fab. Just for comparison, to make an automotive fab, to make a facility to make cars, you need about $1 to $2 billion of investment. And not a lot of companies can do that. The Gigafactory that was built a few years ago to make these batteries for all sorts of applications, that cost about $5 billion. But come back to microelectronic facilities, in 2016, the cost of a fab by TSMC was about $16 billion. And that's already 5 years ago. That's already a technology that is fairly mature, not the leading edge anymore. Nowadays, the fabs are even more expensive than that. And now the challenge here is that because of the pace of the technology, the manufacturers have to basically run these facilities 24/7, 7 days a week. And they have to recover that investment within a few years, because then the next technology comes along and everybody wants to move to that new technology. So they have only a 3-year to 5-year window to recover most of the investment. And after that, the fab is basically considered an older, mature technology. It may not have the same level of profit margins for the manufacturing facility in terms of, customers that will use it. And then it is no surprise that there are only a few companies in the world that can do that, right? So there's a Taiwan semiconductor manufacturing company in Taiwan, Samsung in Korea, Intel in the US was leader, but now they're falling behind a bit. And there's really not too many other names that you can add to that list. Maybe ST Microelectronics, but it's becoming a very, very challenging and expensive process to have the state-of-the-art facility and run it. For MEMS, it's not as bad yet. And one good thing about the MEMS clean rooms is that the resolutions we need is on the order of microns in most cases. We do not really need nanometer level resolution. So that reduces a large amount of, let's say, requirements that you need on the lithography system, which is your fundamental step in all of your manufacturing. And then what that means is that you can use an older microelectronic facility to make MEMS. And that's what a lot of these companies are doing, right? So nowadays that they don't have enough, let's say, customers for a process that was, let's say, 180 nanometer CMOS, Well, they go and change some of the tools there. We'll talk about especially etching the tools. You need new ones. But the rest of the facility can be used to make MEMS devices, or most of it can be used to make MEMS devices. And they're converting some of those older facilities into MEMS manufacturing devices in order to generate new revenue. So please have a look at these other videos. So this one is from TSMC. They are the leaders in technology nowadays. And you'll see that, you know, it's just an amazing arrangement of engineering skills, knowledge, science, and then application. Going back to the photolithography step, we want to see what are the required steps here. At the very beginning, what you do is that you take your wafer and you coat it with a polymer that is photosensitive. So we call it a photoresist. The way that you apply it is that you pour a few drops of photoresist at the center of the wafer and spin the wafer. And the surface tension between the photoresist, the liquid, and the wafer will make sure that it will stick to the surface of the wafer, and by spinning it, you spread the photoresist over the entire surface of the wafer. In order to make sure that your photoresist sticks to your wafer, sometimes you need to do a little bit of surface preparation. And once you're done with the spinning of the photoresist, you have the desired thickness of photoresist on your wafer, you want to get rid of the solvent that you had in the polymer. So you basically bake it. It's called the soft bake. It's maybe 90 degrees Celsius for a few minutes or tens of seconds, just to get rid of the extra solvent that you don't need anymore, and you just are left with a film of the polymer on the surface, the photoresist. Then what you do is that you get one of those mask plates that already has a drawing of the layer and the stuff that you want to keep on your photoresist. Put it on top of this photoresist layer that is, again, on top of your wafer, and expose it to UV light. The photoresist is sensitive to UV light. It could be in two ways, so I'll talk about that in a second. But the pattern that you have on that mask, the chrome lines that you have on that mask, will block some of the light, so some regions of the photoresist layer underneath will not see the light. The rest of it is exposed to that UV light. Depending on the chemistry of the photoresist, two things can happen. If you have a positive photoresist, what will happen is that the areas that are exposed to UV light become more soluble in the developer solution that we will be using to remove unwanted photoresist. So what happens here is that normally the situation is that you have these long polymer chains for your positive photoresist, and the UV light comes and breaks down these chains, and therefore you will have, let's say, it's easier to remove the photoresist once you put it in the right solution after the exposure. You can have the other situation where you have a negative photoresist, in which case the areas that are exposed to UV actually become harder. So the opposite things happen here. The UV light actually makes or lets the material in the photoresist form longer chains of polymers. So therefore, these become harder to remove. And once they're exposed to UV light, those areas will be more difficult to remove from the surface. When you put this wafer inside your developing solution, the areas that haven't seen the UV light will be removed. So the two photoresists, they use different chemistries, but at the end of the story, the end result is that, depending on which one you use, you will have a positive image of what you had on the mask on your wafer, or a negative image of what you had on the mask on the wafer. In the most situations, in most typical applications, we use positive photoresists because of the chemistry is easier and then more suitable for the following processing steps. But negative resists are also are used quite often, especially when you go to e-beam lithography and those kinds of technologies. It is the negative photoresists that dominate the let's say, chemistry. Once you're done with this, your developer has removed the photoresist that you don't want, either positive or negative. You just want to make sure that everything is going to be a little bit more chemically stable. The remained photoresist is more stable chemically, and you do a hard bake. And the hard bake is, again, let's say, You put the wafer inside an oven at, let's say, 120 degrees or so for, let's say, 10 minutes or 15 minutes. And then what it does is that it just makes the remaining photoresist on the wafer more chemically stable, so that in the future processing steps, it's not removed easily, which is critical, because normally the next step that you have after lithography is an etching step that is relatively harsh. Just a few words about photoresist. We mentioned the difference between positive and negative photoresist. So again, a positive photoresist, if you use it, you get a positive image of what you had on the mask left in terms of remaining photoresist. If you use a negative photoresist, you get a negative image of the drawing on your mask left on the wafer. The application process for photoresist, you start by putting a few drops in the middle of the wafer and spinning it. It is also possible in some cases, if you're using diluted photoresist, to spray photoresist on the surface, but you get a very rough surface in most cases. So by just spinning it as shown here, you get really smooth films, which is critical in getting a high resolution from your lithography step. The thickness of the photoresist, as you might guess, is going to depend on a bunch of parameters here. So the first one is concentration, concentration of the polymer in your photoresist, how much solvent you have there, how thick is this photoresist, right? So that is obviously one parameter, so that's indicated by variable C in that equation. Then the next one is that the viscosity of the resist, so same thing, the concentration of the polymer and viscosity usually go hand in hand, but you again expect the viscosity to affect it. And then finally the spinning speed, how fast do I spin this wafer? If I spin it at higher speeds, I expect a thinner film of photoresist on the surface. Now, this empirical formula here gives you that relationship. So these parameters beta, gamma, and alpha are empirically defined or measured. So does the parameter k in front of this. But once you do a few test runs at a few speeds, you can basically create a graph and figure out the thickness of the photoresist at any other intermediate step. Depending on the application and actually how much money you have, you can use different UV sources. We'll see that the wavelength of the light that you use is going to be very important to how small a feature you can pattern. But we give them some names, right? So for G-line, H-line, I-line, these are different structural lines in the UV, in the radiation pattern of the UV light bulbs. And those are the wavelengths that we typically use in a university with a manual mask aligner, as you can see here. This is a photolithography system that we actually have. Both of them are at SFU clean rooms. In a manufacturing facility, things are a little bit different. So the system looks more complicated, more complex. You usually do not have access to any of the components in there. And that system is going to cost about $100 million or more for each one of those lithography systems. The cleaning room, the ones that you see on the right of this slide, these are 100K to 500K. Usually that's the range of prices for them. The one that you use in a manufacturing facility is about $100 million nowadays. So here's a video about the steps in the lithography process. I suggest that you watch it on your own time. So stop the video now, or the lecture video now, have a look at that link, and then come back and we can continue from that point onwards. So depending on what is available to you in terms of system and the resolutions that you need, you have three options for typical photolithography. So typical photolithography is the one that I showed you earlier. So you have a UV light source. UV light goes through a mask that is generally a glass plate with chrome features on it, and some of the light is blocked, some of the light goes through, and the photoresist is exposed underneath that mask. So you have three options here. The first option is that you put the mask right on top of your photoresist, so they actually are touching, and what you see here is that these let me see if I can. So these black areas are the chrome features on the mask. The mask itself is this white plane here, and this is your photoresist. This the hashed area is your photoresist. So you expose this to your UV light source, and what happens is that there is obviously an optical system involved, right? So your UV light source may not produce parallel beams of UV light, so you need to collimate that and make sure that the lines are more or less parallel when they hit your mask, so that you don't have deviations from, let's say, one corner of the mask to the other corner. But because you're you're pushing the mask against the photoresist, these are things that can happen. The advantages is that this is a very simple setup. You just put your mask on top of the photoresist and just make sure that they're in good contact throughout, and you do your photolithography. You can get good resolutions. You know, on a typical mask nowadays, we can have a resolution of at least half a micron, maybe better than that. And whatever the resolution that you have on that mask, you get on your photoresist. They are in touch. However, the disadvantage is that the resolution may not be uniform because you're covering a large area at once. And no matter how good your lithography, how good your optical system above the mask is, you can have a little bit of variation between, you know, the features that are at the corner of the wafer compared to the ones that are closer to the center. So that could be one problem. The other problem is that because the mask and wafer are touching each other, you can have particles on the surface of your photoresist, and they can stick to your mask after you're done one lithography step. Now the problem now, well, the first wafer may go through just fine. The second wafer that comes in will have that particle on the mask, and therefore that region on that mask is going to be, let's say, mispattern. And then the third one, and then the fourth one, and then all of the wafers that you will process out from that point onwards will have that defect on them. We cannot tolerate defects on masks, right? These are the most critical components. Any defect on the mask will be transferred onto all your devices that you make with that mask. So this is a challenge, and also because there's mechanical touch and let's say friction and all that, your mask will wear out over time. So the solution to that is to create a small gap between your mask and your wafer. So what you're doing now is that you bring them very close to each other, but don't let them touch. So let's say you maintain a 50 micron gap. That's 1/20th of a millimeter gap between the wafer and the mask. Obviously, this is not that easy. However, you fix the problem of the two of them touching each other and then, you know, wear and tear on the mask or having a defect on the mask, which is something you don't want. So again, the setup is relatively simple. You know, just creating a tiny gap between the two is not too hard. And your mask is essentially going to last forever now. There's no wear and tear. But you will pay the price in terms of resolution. Because the two are separated from each other, you have more problems with diffraction of light as your UV light goes through the mask before it hits your substrate. So your resolution will suffer. You also have challenges with uniformity now, right? So if you had uniformity challenges with contact printing, now you actually have more challenges in terms of the uniformity of the pattern across the wafer. This is called proximity printing. It's really not used that often. We usually use contact printing in the research labs and university labs, or we use projection printing in manufacturing facilities. So in projection printing, what we do is that we go around the problem of the contact between the mask and the wafer by separating the mask from the wafer. And we go around the problem of let's say, reduced resolution that we had for proximity printing by having a more complicated optical system here. Now the optical system, what we have is the light source, and then there's a lens system to create the collimated beam of light. It goes through the mask, and then we have another lens system to basically reduce the dimensions, to shrink the dimensions, right? So project an image of the mask onto the wafer, but we have an objective lens here that reduces the feature sizes. So if you have, let's say, 10 micron features onto your mask, we go through a 5:1 or 10:1 reduction, and the 10 micron feature on the mask is going to be translated onto a 1 micron feature on your wafer. Now, the advantage is obvious. We can get a high resolution here, right? So if you have 1 micron features on your mask, now you can get 0.1 micron features on your wafer. So this is an obvious advantage. Obviously, the mask is separated from your wafer, so therefore the lifetime of the mask could be much longer than contact printing. Cons, well, this is where the price you pay for all the benefits comes in. It's a much more complex system than the one we just showed about. So what the complexity means is that it's a lot more expensive than the previous system. Now, that's one issue. The other issue is that because we are having a 10:1 reduction in image size, we cannot cover the entire wafer area in one shot. Now you have to expose one corner of the wafer, then move to the next area next to it, then next to it, then next to it. You have to step through these different segments on your wafer. These systems are actually called steppers. So it's a projection system, but it is stepping the wafer underneath the UV light source. And you will see that in your video. So if you check the videos that are included here, you will see these stepping systems. Another challenge we have with these projection systems is that the depth of focus, because of the optical system you use here, is limited. With, let's say, contact printing or proximity printing, you could basically go through the entire thickness of the photoresist with not so much trouble. The UV light, there was not that much issue of, let's say, focusing. Now, because of the lens system, you have your objective lens system, you have them in front of your mask, the image will be in focus for only a very limited range, and that's usually less than a micron. So you have to keep your mask, your wafer within that depth of focus. You have to make sure that your wafer has a relatively flat surface, otherwise you will have different levels of exposure at different depths. Now, once your photoresist has been exposed to UV light using one of those 3 methods that we mentioned, we need to remove it from the surface, the areas that are basically not needed anymore, depending on the type of the photoresist that you use. You need to get rid of the unwanted photoresist. This is called developing, and usually this is the last step you have in photolithography, followed by maybe a soft bake, right? So it includes a soft bake. The next step is usually etching, right? So after the etch, you may have some photoresist left on the surface that you need to get rid of. That usually is done with solvents, but developers are solutions that do not, let's say, if you're using a positive photoresist, do not remove the unexposed areas. Only the exposed areas will be removed. But then at the end of the story, when you want to remove the entire photoresist layer from your wafer, you go and use a solvent, proper solvent to do that. Acetone being one that we use commonly in the university. Now, in terms of resolution that you get out of these processes, you can basically know by now that by using one of those 3 different techniques, we can get different resolutions. For proximity and contact printing, the formula that gives you the resolution is relatively simple and straightforward to understand. So it says the resolution, which is the minimum line width that you can pattern, or the minimum gap that you can have between 2 pattern lines, is given by this expression. So let's not worry about this 3/2 factor here. Lambda is the wavelength of the light. Obviously, if you use the light with a shorter wavelength, you will get better resolution. You will have less problems with diffraction. S is the separation between the mask and photoresist layer. So if it is contact printing, you set S to 0. If it is proximity printing, you put it to whatever that separation is. And T resist over 2 is the thickness of the photoresist that you have divided by 2. And that 2 here is representing the refractive index of the photoresist. Right? So it's as if the thickness of the photoresist, you have to add it to S, but because the light is traveling through a new material, through the photoresist, you have to adjust for that. So that 2 adjusts for the fact that, during the thickness of the photoresist, as the light goes through that thickness of the photoresist, the wavelength of the light will be a little bit shorter. So this is the expression, and you can actually go and use this to calculate the resolution under different conditions. If you increase the photoresist, what happens, the thickness of the photoresist, or if you have the possibility of changing the light source, what can you do with that? But usually lambda is not something that you can change unless you go and buy a new system. For projection printing, things a bit more complicated. It's a complex optical setup. The resolution at the end of the story is given by the formula shown here. In this case, the resolution is directly proportional to lambda. So that is the reason for a push for going to shorter and shorter wavelengths. Because a lot of industrial manufacturing facilities use projection printing. So you go and use a shorter wavelength, you get that much improvement in your resolution, which is really important. Numerical aperture is the ratio of the lens radius to focal length. It's a property of the optical system, and it's somewhere around, let's say, half, 0.5 plus and minus 0.2, 0.3. You usually want to make it as large as you can, so 0.9 if you can, even higher, 0.93 for example. And K1 is an experimentally calculated value, right? So K1 is depending on your system, NA is depending on your system, lambda is about your light source. Depth of focus, we mentioned, is a challenge in your projection printing systems, is given by this expression. Again, K2 is a constant that is determined empirically, but what you can see is that the depth of focus, the important point here is that inversely is proportional to lambda if you take resolution as a constant, or directly proportional to lambda if you use a fixed system with a non-numerical aperture. But again, this tells you how much roughness, basically, how much surface roughness you can tolerate between the steps. And from time to time, you have deposited and etched layers of different materials on your wafer. You will have topography on the surface of the wafer, and it may just adversely affect the resolution of your lithography step, as you can see here. What you need to do is usually go and do a CMP, chemical mechanical polishing step, in order to flatten the wafer and then come back to your lithography step for the next stage. So as we mentioned, in most cases each lithography step is followed by an etching step. In, I would say, 70 to 80% of the situations, maybe even 90% of the situations, there are some techniques where we do not have an etch step for different reasons. So for example, in case of electroplating, we saw that you deposit your polymer film first, pattern it, and then grow the material inside the openings. But in the vast majority of the cases, we use the photoresist pattern that is left on the wafer as a template for what we want to be removed from the layer underneath. So in MEMS, in microelectronics, we would like to keep everything as flat as possible. Usually the etch depth, the film deposition, let's say doping, all of those are sub-micron. In MEMS, in many cases we want to deposit a thick layer, so it could be a few microns in thickness. Or we want to etch very deep into the substrate. We can etch as deep as, let's say, 100 or 200 micrometers. And we're creating true 3D structures out of 2D drawings. And a layout, as I mentioned, is all these 2D drawings put on top of each other and aligned with each other. Now, each mask will have one layer information on it, and each mask has to be aligned with the previous mask, with whatever that you have on the wafer, right? So remember that you have the layout of the device. There is a beam, there is metal right on top of that beam. So the beam is made through one fabrication step, one lithography step. The metal that goes onto it is coming from another lithography step, another fabrication step. These two have to be aligned with each other. So alignment of the mask to features on your wafer is also an important issue. You want to make sure that you're depositing the new material or etching the areas from the right portions of the wafer. Mask alignment is very critical. And actually the lithography step that we have, the system is not called the photolithography machine. In most cases, we just call it a mask aligner. It aligns the mask to whatever features that we have on the wafer. Design rules are important, and layouts are generated by engineers that have to follow the design rules, right? So design rules come from how you make these devices, from the processing steps. We'll go through some of them in the next slides. But layouts can be compared against or validated against the design rules that you may have for the process. There are alternative lithography techniques or pattern transfer techniques to photolithography. Soft lithography is one technique shown here, that you go and you create a pattern, let's say on your mask, put it on top of some soft material. The material will stick to your mask. You just go and print it onto somewhere else. It's like a stamp. You just go and stamp the pattern. So the material that you have here is going to be your ink. You put your stamp here and go and transfer that pattern onto some other material. You can get sub-micrometer resolutions this way. This is a fairly low-cost system. It's just stamping, right? As long as you have the mask, the rest of it is stamping. There's some mask wear and tear, but that's really, in considering the throughput you get, is not that significant. The challenge is, let me talk about the next one and then we'll talk about the challenge. Now, because you're not doing the pattern transfer using an optical system, you can actually do it on a large area. So just stamp one right after the other, or create a big enough mask that you can just have one stamp and transfer all the patterns that you want. An alternative to this is nano imprint. In this case, what you do is that you go and create the pattern on your surface, put your soft material on the surface, press the mask against that material, create the features using mechanical pressure, remove the mask, and then you have now a pattern that matches the wafer, basically a negative image of what you had on that wafer. You can use this template to do the patterning as needed. Again, this can be applied to large areas. This can be low cost and high throughput. Wait for a second and think, what is the disadvantage? If we can, get 10 nanometer, 20 nanometer lines this way, why don't we use it for all of the lithography steps that we have? Why don't we use these two instead of lithography steps that we have in microelectronics or MEMS? And the answer is that you cannot do alignment here. This is only good for the very first stage, right? After that, you cannot do this reliably if you have multiple layers that need such resolutions. So for most situations, we are basically stuck with the photolithography systems that we talked before. Nowadays, there are techniques to improve or tricks to improve the resolution. So remember, lambda was determining your resolution both for projection and contact or proximity printing. One trick that we can use, that we already have talked about it, is that we can fill the gap between the mask and the wafer with a liquid. And by doing so, we make the wavelength of the light will be shorter in that liquid. We should therefore be able to pattern smaller areas, smaller features. This is called immersion lithography that is already in use. EUV, extreme UV, goes and uses UV light sources that are very short in wavelength, right? So 10 to 14 nanometers. So this is again something that is already in use. The challenge is that it's getting harder and harder to find proper light sources at these very extreme UV frequencies. And the other challenge is that when you make a lens, remember that you have this optical system for your projection printing. UV light, if it has so much energy, is absorbed by most materials. So your typical lens material that you used in, let's say, 100 nanometers or higher can be absorbing a lot of the light that comes from your light source just in the lens. X-ray is another choice that people have tried. Again, you can get very high resolutions with X-rays if you use, instead of UV rays, you use X-rays. You have, again, two issues, similar issues, but from another point of view. So again, you have an issue with the light source. You cannot really have wide area, high energy X-ray sources that are collimated that easily. That's one challenge. The second challenge is that the opposite of what you had for UV. X-ray is so high in energy that it just goes through any material, and it's not affected by the lenses that you put in front of it, right? So that's the opposite challenge. It just goes through any material. And therefore, in order to use X-rays for your lithography, you need to use mirrors instead of lenses. It's a new optical system, new way of thinking about all of this. It's a challenge, right? So X-ray lithography is not as common as EUV. E-beam lithography, you use electron beams instead of light, and you use electrons instead of photons to pattern to transfer the pattern onto your mask. It is used a lot nowadays to make those masks that we talked about. So far we talked about this pattern on the mask that you use to basically define features on the wafers, but we didn't talk about where that pattern on the mask came from. Well, those masks, the mask plate is made by having a glass plate, covering it with chrome. Actually, it is chrome oxide or sometimes ferrous oxides, but anyway, some material. Then you use E-beam lithography to define which areas of this chrome you want to keep by covering it with usually a negative photoresist, pattern transfer using E-beam lithography, and then removing the photoresist and then subsequently chrome that you don't need. The challenge with E-beam lithography is that it's a sequential process, right? So you pattern, it's a beam that goes right and let's say draws patterns on your wafer. If you have a large area, it's going to take a very long time, right? It's not like a single exposure, it's continuous writing of features. So therefore, it becomes expensive. Time is money. Also, because you're using electrons, the surface can charge up. So that's another challenge. And then because it is a slow process, the throughput is very small, right? So you do not produce a lot of wafers through this. And again, time is money. The cost per wafer is going to, you're not making as many devices nowadays, so therefore the overall manufacturing cost has to be spread across fewer devices, meaning that the devices will be more expensive. So E-beam lithography is used a lot to make the masks, but not in production. There are solutions, and people are looking for solutions like multi-beam writing and all that, but still not as fast as necessary. Ion beam lithography is a similar situation. Instead of electrons, you use ions, and you get similar resolutions. But as I said, it will suffer from the same sort of problems as well. And now, for the remainder of this lecture materials, we have a video that you should look about the processes that you have in a modern clean room. Now, just to appreciate how challenging these processes are for manufacturing, here is the cost of masks up to 2016. I don't actually have a graph like this for more recent processes, but you can expect a similar type of growth in costs. So in 2016, for 28 nanometer technology, this is 3 or 4 generations before already, the cost of one mask set was $1.6 million, right? So not a lot of companies can afford that. If you're a startup and you tell them that I'm going to spend $1.6 million to get the mask for this chip and there's an error on it, you basically run out of money before you even see your first product. Cost of developing new ICs, this is a little bit more recent. You can see that if I want to go and make a new chip in the latest technologies, let's say 5 nanometer, I have to have about $500 million in my bank account. And I better hope that there is no mistake in my design. So I don't have a chance, or I won't have a chance for redesign. And what that has done is that it makes redesigning very expensive. It makes going to the latest technology for vast majority of applications uneconomical. And what happens and what the companies are doing is that you're going to a 5 nanometer technology or a 7 nanometer technology. It's very, very expensive to make a chip on that technology. Now, let's make the best use of what we have made on that wafer. So what I can do, for example, if I have a 10-core processor on that chip, and I take this out, and after the fabrication, and I notice that one of the cores is not working, right? Something has happened. I have to have that kind of prediction in my design that if one of these cores are not working, I just take it offline. And I sell the rest of the chip as a 9-core processor. That's actually done very commonly, and that's one of the reasons sometimes that you need an odd number of cores, a weird number of cores on a processor, a 3-core processor, a 7-core processor. It's most likely a chip where one or more of the cores on the original design didn't work. Another thing you can do is that you go and make the chip and you see that it is failing the specs that you wanted, but it is meeting the slightly lower specs. So let's say you design a processor to work at, let's say, 3.8 gigahertz, and it fails the test at 3.8 gigahertz, but it passes the test if you drop the frequency at 3.2, 3.4. So you sell it under a different name, different chip number, but at a reduced clock frequency. And you obviously have to put your word behind it. Right? You have to guarantee that it is going to work fine. But sometimes they do. Sometimes in very rare cases, if the chip complexity is not too large, you can actually do a little bit of post-fabrication manipulation. You cannot do that for digital stuff. There's just way too many components there. But for analog chips and MEMS chips, it might be worth it if it is a high-value component. But in most cases, you're just trying to avoid any such manipulation. So that's that for the lithography step. As I said, there are a couple of videos that we skipped. Please go and watch them, or I'm hoping that by this time you've watched them. The next discussion is going to be about etching. We start with the basic etching, which is wet etching, and then we talk about the more advanced way of removing material through dry processes. Thank you.